Hello, I'm Brain Rady, and welcome to my Black Hole Lab. Introduction. Students will alter some given starter code in order to estimate the mass of a black hole. Each student will have a unique star trajectory which is generated by their email. Since students are allowed to assume that the net force on the star is solely due to the black hole, Newton's second law can be simplified to F net equals G big M small m over r squared, and those are all multiplied. Where G is the universal gravitation constant, big M is the mass of the black hole, small m is the mass of the star, and r is the distance between the black hole and the star. And here are my results. The green arrow is F net. The magenta arrow, I guess you could call it, is F net perpendicular, and the cyan one, which gets really small, is F net parallel. And the mass of the black hole this whole time, as you saw, was running. It was being printed constantly, and it was non-constant. And this is due to the fact that the way everything was calculated was through an iteration process of a time step of 1 day. So if I wanted to get maybe a little bit more accurate results where the mass wasn't changing so much, I would choose a smaller time step next time. Here are my data measurements and calculations that I'll go over now. And while most of my data and measurements were calculated through the Python code in GlowScript, I calculated the mass of the black hole using the given data in GlowScript. I pasted all 459 calculated values of the black hole's mass and averaged them to obtain one single mass value as seen here, which was roughly 1.615 times 10 to the 34th kilograms. And here's the beginning of my coding. I first altered the seed by typing in my email. Feel free to hit me up. I then edited the star's mass to the value given in the lab instructions in delta t to how many seconds there are in a day, which is 86,400. In order to create the errors in my model, as seen earlier, I edited the lines 201, 207, so that there would be errors representing F net perpendicular, and F net parallel. Here's the second part of my coding. I followed the steps instructed in the edX video, filling in the lines of code as the video progressed. I was able to do most of it on my own, but some were a little bit tricky, especially in this part. And all of these were derived in class. Like these two up here were just the general momentum formula, which is just momentum equals mass times velocity. These are just delta V, delta P are just changes in those velocities. You take the final and subtract the initial from it. And dp/dt is just change in P over change in T, which is delta P over delta T. And we solved in class that F net is equal to dp/dt. And as I said here, this was a little bit complicated, but you just solve for the p hat in the formula, which is just solves for the unit vector, and the magnitude of dp/dt, or the magnitude p dt is just equal to the change in the magnitude of the momentums over delta t, and then you multiply those together to get dp/dt parallel. And I utilized the fact that F net is equal to F net perpendicular plus F net parallel to solve for dp/dt perpendicular by subtracting dp/dt parallel from dp/dt. And that solved for F net perpendicular because those are equivalent as well. And the mass of the black hole, or MBH formula, was derived by isolating big M in the equation F net equals G big M small m over r squared. And you can see that this is all solved for here. What does it mean? To discuss the net force and how its parallel and perpendicular components are different from the rate of change in momentum and its parallel and perpendicular components, we derived an equation in class that equates the perpendicular force and change in perpendicular momentum, as well as it equated the parallel force and the change in parallel momentum. However, while solving for each value iteratively, these values can only be approximately equal to each other. And this is due to our time step being not infinitely small, and instead it's a whole day. So once again, if I wanted to get these values to be a little bit closer, I would choose a smaller time step so that the iteration process would affect the results a little bit less. What if? And if we were to imagine a black hole whose mass that we found was removed, and then put in a new black hole, and the motion did not change at all of the star, the only force is the gravitational force in the new black hole, could you tell the difference? And the answer is no. And that's because if the motion remains unchanged, that means that the net force on the star has not changed, which means the mass of the new black hole is the same as the old black hole. And that answers the second part of the question. And that's my presentation. Thank you.